At some point in the last few decades, something entered the inner region of our solar system. It was detected briefly, it was logged, it was measured just enough to confirm that it was real. And then it was gone. Not because it exploded, not because it slowed down, not because it hid, but because we lost track of it. This is not a story about something far away. This is not a story about distant galaxies or events that happened millions of years ago. This is a story about something that passed close to the Sun, inside the region where we assume our detection systems are strongest. And we still lost it. In astronomy, losing an object is not supposed to happen easily. Every known planet, asteroid, and comet inside our solar system follows predictable rules. They orbit, they reflect sunlight, they move along paths we can calculate years in advance. Once detected, they are usually tracked continuously. But this object did not behave that way. For a brief window of time, astronomers knew it was there. They could estimate its speed, they could determine its direction, they could tell it did not originate from Earth. And then it slipped out of view. That moment, the moment of loss, is more important than the moment of detection. Because detection proves our instruments work. Loss exposes where they fail. Astronomers are trained to think in probabilities, not certainties. They understand that the sky is vast and their coverage is incomplete. But the inner solar system is supposed to be different. This is where our telescopes are optimized. This is where potential threats are monitored. This is where we expect awareness. And yet, this object moved through that space faster than we could adapt. The first assumption was simple. The object must have been small. Small objects are harder to track. They reflect less light. They fade quickly against the brightness of the sun. But size alone does not explain everything, because even small objects leave traces. And this one left just enough to confirm it existed, and just little enough to escape. This raises an uncomfortable question. If we can lose an object after detecting it, how many objects do we never detect at all? Most people assume that near-Earth space is constantly watched, that powerful telescopes scan every direction, that nothing significant can pass nearby without triggering alarms. That assumption is wrong. Our detection systems are not designed to see everything. They are designed to see specific things, in specific regions, under specific conditions. They look outward, away from the sun. They favor slow-moving objects. They struggle with glare, speed, and geometry. And this object exploited every one of those weaknesses. The truth is uncomfortable. We did not lose this object because we were careless. We lost it because our system was never built to hold on to it. In the coming minutes, we are going to examine what astronomers actually detected, how close this object came, why tracking failed so quickly, and why similar losses may be happening far more often than we realize. This is not a story about mystery. It is a story about limitation. And once you understand those limitations, you may start to question how much of our own cosmic neighborhood we truly understand. When astronomers say an object was detected, that does not mean it was photographed clearly. Most detections begin as anomalies, a point of light where there shouldn't be one, a faint streak across a survey image, a short-lived signal that does not repeat. That is how this object first appeared. The detection came from sky surveys designed to monitor near-Sun regions and near-Earth space. These surveys are not looking for mysteries. They are looking for hazards, asteroids that could cross Earth's orbit, comets approaching from the outer solar system, objects whose trajectories matter. And for a brief moment, this object mattered. Based on its apparent brightness and motion, astronomers could immediately tell three things. First, it was moving fast. Fast enough that its position changed noticeably between observations. Second, it was on a steep trajectory relative to the plane of the planets. It was not following the familiar flat paths of most solar system bodies. Third, it was close to the Sun. Uncomfortably close. This is where detection becomes difficult. Objects near the Sun are hard to observe for a simple reason. The Sun is bright. Its glare overwhelms faint reflected light. Telescopes must avoid pointing too close to it, both to protect their instruments and because the background noise becomes extreme. As a result, there is a wide region of space near the Sun that is poorly monitored, and this object passed directly through that region. From the limited data available, astronomers estimated its distance. It was not grazing Earth's orbit. It was not a distant outer solar system visitor. It passed well inside the orbit of Mercury. That places it closer to the Sun than most objects we routinely track. At that distance, everything happens quickly. Orbital speeds increase dramatically. Small errors grow fast. Tracking windows shrink. A delay of hours can mean the difference between continued observation and permanent loss. For a short period, astronomers could predict where the object should be. They attempted follow-up observations, but each attempt faced the same obstacle. The object was fading, not because it was slowing down, but because its geometry was changing. As it moved relative to Earth, the amount of sunlight it reflected toward us dropped sharply. It became lost in solar glare. And once it crossed that threshold, it was effectively invisible to ground-based telescopes. This is the critical point. The object did not vanish mysteriously. It vanished predictably. It crossed into a region where our instruments are weak. And by the time it emerged on the other side, it was already too far away and too faint to recover. Astronomers refer to this as a lost object, not because it no longer exists, but because its orbit can no longer be refined. Without additional observations, uncertainty grows rapidly. Within days, then hours, its possible location expands across vast regions of space. Eventually, it becomes unrecoverable. This happens more often than most people realize, but rarely with objects this fast, and rarely with objects this close to the Sun. The detection, brief as it was, told us just enough to confirm something important. This object was not an illusion. It was not noise. It was not a data artifact. It was a real body moving through the inner solar system faster than our ability to adapt. And that forces a troubling realization. If this object had been slightly larger, slightly darker, or arrived at a slightly worse angle, we might never have seen it at all. That realization is where the story truly begins. Because this object was not unique. It was simply one of the few that briefly crossed into our awareness. To understand why this object was lost so quickly, you have to understand how we actually observe the solar system. Most people imagine telescopes constantly watching every direction. That image is wrong. Ground-based telescopes are designed to look away from the Sun. They operate at night. They avoid bright backgrounds. They rely on contrast. Near the Sun, contrast disappears. Any object approaching from the direction of the Sun is effectively hiding in daylight. Its reflected light is drowned out. Even large objects can become invisible against the glare. This creates what astronomers openly refer to as a solar blind spot. This blind spot is not small. It spans a significant region of space inside Earth's orbit. Objects moving through this region can approach, pass close to the Sun, and exit again before detection becomes possible. The geometry matters. If an object approaches from behind the Sun relative to Earth, it is almost guaranteed to remain unseen until it is already moving away. By then, it is fainter, faster, and harder to track. This is not a theoretical concern. It has happened before. Multiple near-Sun objects have been detected late, or not at all, because of this exact limitation. Some were only noticed after they had already passed their closest approach. Others were detected once and then immediately lost. Speed makes the problem worse. Objects near the Sun move faster than objects farther out. Their orbital velocities increase sharply as distance decreases. This compresses observation windows. A delay of a single night can be decisive. The object in this case combined every unfavorable factor. It approached near the Sun. It moved quickly. It was faint. And its trajectory minimized reflection toward Earth. Once it slipped into the solar blind spot, follow-up observations became nearly impossible. Telescopes could not safely point closer. Space-based assets were limited, and prediction uncertainty grew too quickly. This is where the idea of losing an object becomes unavoidable. The object itself does not disappear. What disappears is our ability to know where it is. Astronomers describe this as an expanding uncertainty region. With each hour that passes without new data, the object's possible location spreads across a larger volume of space. Eventually, that volume becomes too large to search efficiently. At that point, recovery is effectively impossible. What makes this uncomfortable is not that the blind spot exists, it is that we have known about it for decades. The solar blind spot is a recognized vulnerability. It has been discussed in planetary defense planning. It has been acknowledged in technical papers, but it has not been fully resolved. Why? Because observing near the Sun is difficult, expensive, and technologically demanding. Ground-based telescopes struggle. Space-based telescopes require specialized orbits and heat shielding, and coverage is still incomplete. As a result, a portion of our own solar system remains poorly monitored. Not because of ignorance, but because of physics, geometry, and cost. This object passed directly through that gap. Not by chance, but because that gap is always there. When most people hear that astronomers lost an object, they assume it was a rare mistake, something unusual, something embarrassing, something that doesn't happen often. That assumption is incorrect. Objects are lost in the solar system more frequently than most people realize. Not planets, not major asteroids, but small, fast-moving bodies that appear briefly, are logged, and then fade beyond recovery. Astronomical surveys detect thousands of new objects every year. Many are tracked successfully, but a significant fraction are observed only once or twice before disappearing from view. They are recorded, labeled, and then quietly marked as lost. This happens for predictable reasons: limited observation time, unfavorable lighting, poor geometry, rapid motion. Each factor alone is manageable. Together, they can overwhelm even modern detection systems. Most of these losses do not attract attention. They involve objects that are small. They pose no immediate threat. They generate no headlines, so they pass unnoticed outside scientific databases. But the frequency matters, because every lost object represents an incomplete picture of our local environment. Each one is a data gap, and data gaps compound. There is also a selection bias at work. We tend to notice only the objects that behave as expected, those that move slowly, those that follow predictable orbits, those that reflect enough light to stay visible. Objects that move too fast, arrive from unusual angles, or pass near the sun are underrepresented in our catalogs. Not because they are rare, but because they are harder to keep. This means our understanding of near-sun space is incomplete by design. We know more about distant regions of the solar system than we do about some areas close to the sun. That imbalance is not intuitive, but it is real. There is another reason you rarely hear about lost objects: language. Astronomers are careful in how they describe uncertainty. An object is not announced as lost publicly. It is described as having an unconstrained orbit, or insufficient follow-up, or limited observational arc. These are accurate terms, but they soften the implication that something passed through our neighborhood and we no longer know where it is. This is not negligence. It is the normal outcome of working at the limits of detection. However, when we talk about planetary defense, awareness, and preparedness, these normal outcomes matter, because systems are only as good as their blind spots. The object discussed earlier stands out not because it was lost, but because it was lost after being clearly detected near the sun. It crossed from awareness into uncertainty in a matter of days. That transition is easy to overlook, but it should not be ignored, because it reveals a pattern, and patterns deserve attention. Not all objects in the solar system are equally visible. Some are easy to detect. They move slowly. They reflect plenty of sunlight. They follow familiar paths. Those objects dominate our catalogs. But the objects we miss tend to share a very different set of characteristics. They are fast. They are small. They arrive from unusual directions, and they spend very little time in places we are watching. Speed is the first problem. Objects that pass close to the sun accelerate dramatically. Their velocities can double or triple compared to bodies farther out. This reduces the time astronomers have to notice, confirm, and track them. Sometimes that window lasts only a few days, sometimes only hours. Size is the second problem. Smaller objects reflect less light. They can appear only briefly, even when relatively close. Against the brightness of the inner solar system, they fade quickly. By the time follow-up observations are scheduled, they may already be gone. Trajectory is the third problem. Most known asteroids orbit roughly in the same plane as the planets. Our detection systems are optimized for that geometry. Objects arriving at steep angles, from above or below the planetary plane, are harder to catch. They cross monitored regions quickly and unpredictably. Some objects combine all three disadvantages. They approach fast, they remain faint, and they arrive from directions our surveys do not prioritize. Those are the objects most likely to be detected briefly and then lost. There is also a category that challenges assumptions even further: interstellar objects. Unlike typical solar system bodies, interstellar objects are not bound to the sun. They pass through once. They do not return. Their velocities are higher. Their trajectories are hyperbolic, and their arrival directions are essentially random. The first confirmed interstellar visitor demonstrated how difficult these objects are to study. By the time astronomers realized how unusual it was already leaving. And by the time follow-up plans were made, it was gone. That event forced a reassessment, not of whether such objects exist, but of how often they pass through unnoticed. The uncomfortable answer is that we do not know, because detection bias hides exactly the objects we are least prepared to track. Most surveys are optimized for persistence. They favor objects that stay visible. They favor repeat detections. They favor predictability. But the objects that pose the greatest observational challenge do not behave that way. They are transient. They appear briefly. They leave quickly. This does not mean they are dangerous, but it does mean they are underrepresented in our understanding. And when underrepresentation combines with proximity, it becomes a blind spot worth examining. The object that was detected and then lost fits this pattern precisely. It was not extraordinary in size. It was not extraordinary in brightness. What made it significant was how perfectly it exploited every weakness in our system. And that raises a critical point. We are very good at finding what we expect to find. We are much worse at finding what does not conform. There is a subtle but important distinction that often gets lost in discussions about space. Detection is not the same as awareness. Detection is the ability to notice something briefly. Awareness is the ability to understand its behavior over time. One does not guarantee the other. In this case, detection gave us confidence. We saw the object, we logged it, we measured it. For a moment, it felt like success. But awareness requires continuity. It requires repeated observation, refined orbits, predictive models, and that continuity never materialized. This creates a dangerous illusion. The illusion that because something was detected, it was under control. In reality, detection without follow-up can create false confidence. This is not unique to astronomy. It happens in every system that monitors complex environments: air traffic control, weather forecasting, cybersecurity. Brief detection does not equal comprehension. The same applies here. We detected an object in the inner solar system, but we did not understand its trajectory fully. We did not know how long it would remain observable. We did not know when it would leave our detection window. Once it disappeared, awareness collapsed. Not gradually, immediately. This is why the object's loss matters more than its discovery. Discovery proves capability. Loss reveals limitation. There is a tendency to assume that technological systems fail only at their edges, that they break in rare, extreme cases. But most failures occur in transitions, between visibility and invisibility, between detection and tracking, between confidence and uncertainty. The object passed through exactly such a transition, and our systems were not designed to slow that transition down. This forces a re-evaluation of what preparedness actually means. Preparedness is not just about seeing something once, it is about sustaining attention. In planetary defense discussions, the emphasis is often placed on size. Large objects are dangerous, small ones are dismissed. But size is only one variable. Speed, trajectory, and timing matter just as much. An object that is small but fast, poorly lit, and geometrically unfavorable can defeat detection systems more easily than a large, slow-moving body. That does not make it a threat, but it does make it invisible. And invisibility creates uncertainty. The uncomfortable truth is that our sense of awareness about the inner solar system is shaped by what we are able to see consistently.
We lost the signature
What
at
falls
grid coordinate
outside
gamma
that
6.
consistency
Rerouting
feels
LiDAR for a
rare,
localized sweep.
even when it is not. The object we lost did not exploit a flaw. It revealed a boundary. And boundaries are where assumptions break.
If we adjust the dark matter halo parameters here, the rotational...
The loss of this object did not go unnoticed within the scientific community. It reinforced a problem that astronomers and planetary defense experts have been discussing for years. Not whether we can detect objects, but whether we can detect them in time. In response, Efforts are underway to reduce the blind spots we have identified. New telescopes are being designed with wider fields of view. Some are optimized to look closer to the Sun. Others prioritize rapid follow-up, reducing the delay between detection and confirmation. Space-based observatories play a critical role in this effort. By operating outside Earth's atmosphere, they can observe regions of space that ground-based telescopes struggle to monitor. They are not limited by daylight in the same way. They are not blinded by atmospheric scattering. But even these systems have limits. Coverage is never complete, observation time is finite, and the solar system is dynamic. There will always be regions we cannot watch continuously. There will always be objects that arrive at unfavorable angles. There will always be moments when something passes through faster than we can respond. This is not a failure of science. It is a reflection of scale. Our solar system is vast. Our instruments, no matter how advanced, are selective. They cannot watch everything at once, and they never will. What matters is not eliminating uncertainty. That is impossible. What matters is understanding where uncertainty lives. The object that was detected and then lost did not expose negligence. It exposed assumptions. Assumptions about coverage, assumptions about proximity, assumptions about awareness. Those assumptions are now being questioned. Quietly, deliberately, without panic. This is how science progresses, not through certainty, but through the careful mapping of its own limits. Some objects will still pass through unseen. Others will be detected too late to track fully. That will continue. The difference going forward is not perfection. It is humility. Because the most important lesson from this event is not that something was lost. It is that we noticed the loss. And that awareness, incomplete as it is how understanding begins.